when we have a differential equation, we can generate a slope field. Now, obviously, we wouldn't generate a whole field because that would take way too long. But this is very easily done by computers now. But what we want to be able to do is at least find the slope sections to given different coordinates. So here, I've been given the derivative. The slope function is y over x. Okay, so if I have y over x, what I can do is I can take these x and y coordinates and draw slope sections. For example, at this point here, 4 over 5 up, okay, it's going to be 4 over 5. So I've got a slope kind of like that. At this point here, it's 2 over 3 up, or slope is 2/3. Okay, so it's a little less steep. Okay, it's kind of hard to draw, but again, it's just an estimate. Let's say that's 2/3 there. At x is 1, y is 0. Okay, that is going to be a vertical. Anything y is 0, we're going to get a vertical tangent. Okay, here x is 2, y is -3. It's the same slope, but positive here. Okay, sorry, negative. Here x is 4, y is -5. So it's a little bit steeper like this. It's essentially symmetrical. It's going to look kind of like that. So we end up getting these. We should be able to, we could have a whole field of this, but that would take a long time. But we can at least find slope sections at any given point by just plugging into the slope equation. So we also want to solve this general solution. So if I solve this, I'm going to separate and integrate. Okay, so when I separate and integrate this, integrate this side, I get y squared over 2 equals x squared over 2 plus c. I'm going to say that x squared minus y squared equals, and let's move the plus c to the other side. So times 2, so it's going to be -2c. So basically this, when I solve this differential equation, this is an equation of a hyperbola. Okay, with a trans, depending on the c, it could be trans x or trans y. If c is positive, it's trans y. If c is negative, it's trans x. And you can see that, yeah, that would generate, okay, this is a hyperbola, yeah. This slope field is indicating that it could be a hyperbola. Okay. So what about this one here? We have the differential equation. Okay, so we're going to calculate the slope field. We're going to generate a slope field by calculating slopes. So plugging in these coordinates, 1, 1, so we get slope of 2. Y is 0, x is 1, we get a slope of 1. Y is -1, x is 1, we get a slope of 0. Here we're going to get a slope of 0. Y is 0, x is -1, so we're going to get a slope of negative. And y is 1, x is -1, so we get a slope of 2 like this. So there's our slope field. Okay, this is not the whole field, we're just sketching slope segments. But if we continue doing that, we can generate a whole field. But we can also solve this differential equation. So because this one is a solvable differential equation, it makes it a little bit easier. So we're going to end up with dy over 1 plus y is equal to dx over x. Integrate both sides. Okay, I want to get rid of the log, so I'm going to put the plus c inside the log. So it's going to be 1 plus y equals log, I'm going to make that kx. Okay, so basically what I've just said is c is equal to log k, and then I use log rules to put that k into the log. Okay, so then drop the logs, y equals kx minus 1. So basically this is going to generate linear equations of different slopes depending on where my x and y is. So if x is, let's say x is 1, y is 0, okay, x is 1, y is 0, k would be 1. Okay, so then we have slope of 1, and this gives us the linear equation of y equals negative x minus 1, so that's going to be that line there. So that we're going to get a whole series of linear equations that go through those different points. Okay? Okay. Oh, this one here is actually asking us to find the actual particular solution. So let's do that. So f of negative 1, okay, is equal to 1. So this one here, we're going to do it through that point. It looks like it's going to have a slope of 2. So if I plug in y equals 1, x equals negative 1. Okay, so we're going to solve for the slope here. So we get 2 equals negative k equals negative 2. So then my particular solution becomes y equals negative 2x minus 1. And that is going to be that line right there. Okay, and that's the solution that goes through that particular point of negative 1, positive 1. Okay, and our slope field kind of indicates that that's in fact true. Okay, we actually found the slope from the derivative, and we actually found the slope from the actual function, from the solution to the function. So they both correspond to each other.